Intersection of two lines. And before we get to the notebook videos and all the notes, I wanted you to try and visualize what's going on. So I'm going to try and visualize it, representing it here. So we're going to represent two lines with two pencils. So I've got a blue pencil and a yellow pencil. I'm going to try and demonstrate it on the ceiling behind me as if that's a piece of paper or something. Okay, so if we have two lines, we know that two lines are always going to touch, provided they're not parallel. So if they're parallel, they're not. But as soon as I tweak one, eventually, as we get closer, and remember, lines go on forever, they're going to touch. It's a little bit more obvious when I have them like this, and then obviously they're going to touch. And where are they going to touch? They're going to touch at a point. So our goal here, when you're finding the intersection of two lines, is where is that point where they touch, okay? And as long as we know that they're not parallel, even though these two don't look like they're going to touch, remember, these will go on forever in both directions, so eventually they will touch. And that point is what our goal is. Now, there are two other cases. You could have these two lines, and maybe they are parallel, okay? So before you go off trying to find the intersection, we better investigate whether they're parallel, because if they're parallel, we know there isn't going to be an intersection. So the first thing you got to do is check to see if they're parallel. How are you going to see if they're parallel? You're going to check their direction vectors. If the direction vectors are scalar multiples of each other, they're parallel. Now, just because they're parallel doesn't mean that we've got this situation, because they could be parallel and actually the same line. Remember, it's difficult to tell if the lines are actually the same. They could be parallel and be like this, or they could be right on top of each other. So we have to be able to tell if they're parallel and distinct, which means they're separate. They are their own line. They're distinct. Okay, so you're going to check whether the direction vectors are the same, scalar multiples of each other. If they are, they're either parallel like this and they're never going to touch, or they're parallel and the same, and they would have infinite intersections. If they're the same line, they're right on top of each other and you can't tell, and they touch everywhere. Okay, if they're distinct, then you know there's going to be no intersection. So before you go off and investigate the intersection of lines, you have to decide if they're parallel and distinct. If they're not parallel, then good news, they're going to touch, and we got to find where that point is. Okay? All right, good luck with the notes.
Thanks, Mr. Lee, for that awesome introduction. So we're going to investigate these two lines. And as Mr. Lee just said, what we need to do is try and compare their direction vectors to find out if they're parallel. Because if they're parallel, then we have something else to look at. We want to find the ones that are not parallel, because when they're not parallel, they're going to intersect. So how do we check? We're going to check the direction vector. So the direction vector are the coefficients of the scalar multiples here. So there's a 1 there and a 1 there. So the direction vector of this guy is 1, -1. And the coefficients of this is -2 and 3. So they are not parallel. Good. So that means we actually have an intersection of lines. So they're not parallel. And therefore, if they're not parallel, they must be different lines. Okay, and so since they're not parallel, they're going to touch. Eventually, they're going to touch. So when they touch, there is a spot, an X and a Y spot, where they have the same coordinates. So the intersection must be where the X's and the Y's are the same. Okay, that it would be the only spot where these two would have the same X and Y, would be the spot where they actually cross. Okay, and that would be the intersection point. So if the X, we're going to assume they intersect, and it says they're going to intersect. So that means their X's and Y's must be equal. So this X must be equal to this X. And so let's actually set them equal to each other. Okay, if this is equal to X and this is equal to X and they're the same, then 1 plus R must be equal to 3 minus 2S. The same with the Y's. The Y's are equal. That means this is going to equal that. So we're going to have -4y, or -4 minus r is going to equal -1 plus 3s. Okay, so here we have the situation where the x's and y's are equal. So we have to figure out, we have to solve this little scenario. So I'm wondering if this looks familiar to anyone. Well, no one seems to be answering me. So what if I rearrange this? What if I put all the letters on this side and the numbers on the other side? So if I took the letters over here, this would be R, and I'm going to bring this -2s. I'm going to add 2s to both sides, and do the inverse operation. I'm going to get +2s. And I'm going to take the number over here, so it's going to be 3, and that's going to become a minus 1, so this will become a 2. Let's put the r's and s's on the same side over here. So this is negative r, and this plus 3s becomes across, it becomes minus 3s, equals, and then this negative 4 is going to come across and become plus 4, and so if we have negative 1 plus 4, we get 3. Now does it look familiar? What? Still nothing? Nobody's responding. What if I did this? Oh, now this looks familiar. If you recall, this is solving an equations, solving 2 equations and 2 unknowns. You have 2 equations and 2 unknowns. And remember, you label these, and you had 2 methods to do this. You could do substitution, or you could do elimination. So you're probably racking your brain trying to remember this stuff from grade 10. How to do elimination and substitution. We're going to do elimination all the time. It's going to be the easiest for what we're doing, and it's going to be extremely important for today's lesson and for next unit. Okay, so we got to remember our grade 10. So I'm going to walk you through these steps, but we're going to have to get really good at remembering what we learned in grade 10. So our elimination is, our goal is to eliminate one of the variables, either the r or the s, so that we could solve for the other one. What you do is you modify either equation 1 or equation 2, or maybe you modify both of them so that you can add or subtract the equations to eliminate a variable. Well, I've purposely set this one up that it's going to be really easy to eliminate a variable. Look at r and negative r. Remember, if they have the same coefficient, if I added these equations and I did 1 plus 2, the r's are going to eliminate. Okay, sometimes you might have to multiply the first one by 2 or 3 or 6 or something like that, so that you get the same letters and same numbers lined up, and so that you can eliminate. Excuse me, sorry. All right, so we're going to add these. So if I add these, this is why I like to have these nice and lined up. Negative r plus r, negative r, they're going to eliminate. What is 2s plus negative 3s? Well, that's negative 1s. And then equals, and you're going to add the number parts too. 2 plus 3 is just 5. So we've eliminated this by performing this operation, equation 1 plus equation 2. And we've got this statement. Now we can solve for s, divide both sides by negative 1, and s is equal to negative 5. So what we figured out is s is equal to negative 5. Now what you normally do is you take this s and you plug it back in to figure out r. But in this particular question, we don't need to do that. We've got an s value that is going to tell us where the x and y's are equal to find the point of intersection. So I'm going to take s here and substitute it into either line 1 or line 2. Well, is it going to go into line 1? Well, no, because that's an r. I'm going to take the s and sub it into line 2. So I'm going to take this and sub it into line 2. Okay, and now I've got the coefficient or the scalar multiple that is going to get me the x and y values that equal to this one. So I'm going to take our thing, and there's x, x equals, and you'll see it's 3 minus, where's the minus? There we go. 3 minus 2s, but I now know that s is negative 5. So I'm going to plug that in. Negative 2 times negative 5 is negative 10, or positive 10, excuse me, and negative times negative is positive. 3 plus 10 is 13. So I figured out the x value. Let's plug in that s equals negative 5 into y. So y equals negative 1s, or sorry, negative 1 plus 3s. Well, the s is negative 5. So it's 3 times negative 5 is negative 15. Negative 1 minus negative 15 is negative 16. And so I found my point of intersection is 13 and negative 16. Because I set them equal to each other, this is the s value that makes this xy equal to this xy. And that is my point of intersection. Okay? So we have to remember how to do elimination from grade 10. It's going to be important, not just here, but in the rest of the units. All right, let's look at another example. So this one, you can tell, is much bigger. I've left myself a lot of space, and we'll see why it's a little bit more difficult. So the first thing you should notice is this question was in 2 dimensions, xy, xy. There was no z value, so it was just 2 dimensions. So it was a little bit easier to solve. This one is in 3 dimensions, in 3 space. Also, this equation is not in parametric. Look at this. When it's in parametric, it's really easy to make the x's equal and the y's equal. When it's not in parametric, it's difficult to see. So I have to take these two equations and put them in parametric before you can even start this question. Okay? So now, actually, even before I want to do all that, I'm going to make sure they're not parallel, because if they're parallel, it'll save me a whole lot of work. So let's check the direction vectors. So the direction vector of this guy is 3, 5, 4. And notice that I've at least saved you this much work. I put this equation in friendly form. It's not in proper form because the negatives are on the bottom, but it's in friendly. So it's easy for me to see the direction vector is -1, 2, and -3. So I look at these. Are they scalar multiples of each other? No, they're not. So they're not parallel. That means they must touch. All right. So I got to figure out the spot where they touch. Well, to do that, I got to put it in parametric. And to put it in parametric, I need a direction vector, but I also need a point from line 1. So what's the point? Well, the coordinate point from the top, remember, is opposite to what you think. The coordinate point is 1, 0, -3. So there's point 1 is 1, 0, -3. Goes to show how important those first few days of this unit are. All right, what's the point here? 0, -9, -1. So 0, -9, -1, opposite to what you see there. All right, so now that I've got my direction vector and my point, I can put it in parametric form. So what does L1 look like when it's in parametric form? Well, let's first look at the x's. It's going to be 1 plus some scalar multiple of 3. So I've chosen the letter R, 1 plus 3R. Now let's compare the y's. 0 plus 5R. Well, I don't need the 0 part, so I'm just going to write that. Now let's compare the z's. -3 plus 4R. All right, and now I've got this line in parametric form. It's easier to work in parametric form. Let's do the same thing over here. Line 2, okay, the x's, again, 0 plus -1, and I've chosen t for this one just because it's a different question, so I've chosen a different letter. Let's check the y's, -9 plus 2t, and the z's, -1 minus -3t. Because the equations are in parametric and they're non-parallel, they are going to touch. We just got to figure out where they cross. And so I got to find the coordinate where this x, y, and z is going to equal this y, x, y, and z, because that's the spot where they will equal. So I've got to solve the x's being equal, 1 plus 3r equals -t, the y's being equal, 5r equals -9 plus 2t, and the z's equal. All right, -3 plus 4r equals -1 plus 3t. So that looks like 3 equations and 2 unknowns, but we're going to rearrange it into the way that I saw it in grade 10, which means I'm going to take this over and bring it over here. I'm going to do this a little bit quicker just to speed up the length of this video. It is a long video, so I'm going to speed it up here. So I'm going to bring this across, make it plus, and I put this over to the other side, makes it negative. This is a 2t. I'm going to bring it across, it becomes negative. This -9 is there, it stays there. And then this -3t comes across, becomes positive. This becomes a +3, and we get that. And now I've got equations 1, 2, and 3. Well, in grade 10, we never had this situation where we had 3 equations. That's weird. And in fact, it's overkill. I only need 2 equations when I have 2 unknowns. If I have 2 unknowns, I need 2 equations. I've got 3. So I don't need all of these to solve my R and my T. So what I'm going to do is I'm going to ignore one of the equations and pretend it's a question like the other one where I only had 2 equations. And we get to be selective about which one we want to ignore. We're going to ignore the one that's going to be the hardest to solve. So if you look at this, this has got a 4r and a 3t. So I think I'm going to ignore the third one and look at the first 2. And I think it's going to be hard to eliminate the r, but I might be able to eliminate the t. If only this was a 2t, then when I added it to -2t, it would eliminate. So how do I do that? Well, I take equation 1 and I multiply it by 2. So this should start to sound familiar from your grade 10. So I'm going to write everything down by 2. And the second equation, I don't need to do anything. I'm just going to just do it that. You could say multiply by 1, but I'm just going to leave it like that. All right, so I'm going to take the first equation and multiply by 2. So that's 3r, so it's going to be 6r. This is going to become a 2t, and that's a -2. And when I multiplied it by 2, it looks like a new equation. So I'm going to call it 4. Okay, This is something I really like to do to keep things organized. I renumber all the time just to help organize my thoughts. So it's the same as number one, just twice as big. So I've called it number four. And number two, I haven't done anything. And I've just written it down. Now, you don't have to rewrite this down here. You might think that's a bit of overkill, but I like to have the equations line up so it's easier to add or subtract. So I'm going to recopy this down here. And just because I'm a little bit picky like this, I'm going to renumber it number five. I don't have to. I could have just left it as a number two and done something with four and two. But I like the one, two, three, four, five. So I like to renumber it. Okay, so now what step do I have to do to these equations to eliminate the t's? Well, if I add them, 2 plus negative 2 is going to disappear. Sometimes you might subtract them if the signs are the same, but some of you might like to make the signs opposite so you can always add. So I'm going to add 4 plus 5. All right, so adding 4 plus 5 is going to disappear the t's, but it's not going to disappear the r's. So 6 plus 5r is 11r. The t's have eliminated. And negative 2 plus negative 9 is negative 11. Oh, isn't that great? Divide both sides by 11, and I get r equals negative 1. Now, this r value, you could sub it back in, but we've ignored this third case. You cannot ignore the third case. We ignored the third case to solve for r, but we have to consider that third case. So it has to satisfy all three. So I am actually going to now have to figure out the t-value. Okay, I didn't have to figure out the t-value in the other question. I do in this question. So I'm going to take r and sub it into 1. Now I'm going to sub it into 1 or 2 because remember, I used 1 and 2 to get these ones. I've ignored the third value for a second. It's going to come into play in a second. But right now, I only used 1 and 2, so I can only sub it into 1 and 2. I'm going to pretend that 3 is not there for a second. All right, so I'm going to take r and sub it into 1. I just picked 1 because it looked a little bit easier. So if I take it into number 1, it's 3r. r is negative 1, so it becomes negative 1. And then quickly seeing that is negative 3, bring that across, becomes plus 2, and I've got my t-value. So I used 1 and 2 to solve for r and t. So I could take t and sub it in here to get my point, or I could take r and sub it into there. But remember, I did all this by ignoring 3, but it has to satisfy 3. So there's an extra step I have to do because this has got 3 equations. And that is I have to verify that these 2 points, which only came from the first 2 equations, also work for the third equation. So I have to check that they also verify into 3. So how do I do that? Well, I do the left side and the right side. The left side of this equation is 4r plus 3t, and the right side is 2. If I substitute in these numbers, so r is negative 1, t is 2, so 4 times negative 2 is negative 4, 2 times 3 is 3 times 2 is 6. What's negative 4 plus that? And that equals, that equals 2. And look, it verifies to the right side. So what that means is I have successfully found the proper r and t that works for equation 1, equation 2, and equation 3. And I needed to verify it would work in the third equation. Okay? Once I have the verification, I know that the left side equals the right side, and I now found my proper r and t. Okay? So now once I have r and t, I can choose whichever one. I could take t and plug it in here to get my x, y, z, or I could take r and plug it into there. I'm going to guess that I put r in. Yeah, r is a little smaller number, so I put it into line 1. Okay, so to do that, you're just going to plug in the r value of negative 1. So 1 plus 3 times negative 1, so that's going to be 1 minus 3 is negative 2. Plug the r into y, so that's going to be 5 times negative 1 is negative 5, and plug the z in 1 into z to get negative 7. And the point of intersection then is negative 2, 5, negative 5, negative 7. As I said, I could have taken t and plugged it into L2. And let's check. Negative 1 times 2, that's negative 2. Good. Put in 2 e's here. 2 times 2 is 4. Negative 9 plus 4 is negative 5. put in 2 here is negative 6. 1 minus 6 is negative 7. So it would have worked as well. Okay? So a lot of steps just to solve this point of intersection. Now, I'm just going to recap one thing. I chose 1 and 2 to solve for r and t. If you chose 1 and 3, you only use 1 and 3 to get r and t, and then you would have to verify into number 2, the one that you ignored. Mine, I used 1 and 2 to get r and t, and only 1 and 2, and then I verified in 3. Similarly, you could have used 2 and 3 to get r and t, and then verify in 1. Whatever is easiest. Okay, you might want to pause and take a break, but I'm going to keep going. Let's do a third example. Now, I'm going to speed this up, do a lot of the math a little quickly because I just want to get through all of the examples. So let's check these ones. Okay, the direction vector 1, negative 1, negative 1, and the direction vector 0, 1, negative 1. They're not parallel, they're going to touch. Okay, good. And I've actually chosen these two that are a little bit easier. So they're going to touch where x and y are equal. X's are equal, y's are equals, and z's are equal. So I set them equal to each other. Rearrange. So I'm going to put all the letters on this side, numbers on the other side. So you see this negative 1 becomes over here. This negative r, this k becomes minus k. And the 2 comes across and subtracts, so it'll be 0. And this negative r stays there. The minus k becomes a plus k. And negative 5, and this becomes minus 1 is that. Okay, so we've just sped through that a little bit. And I'm going to try and solve 3 equations. So I'm going to only take 2 of them. But wait, this one actually worked out even easier. I already figured it out. So I got one of my values right away. I didn't need to do any eliminating. The k was already eliminated. So I've already solved the r. So I'm going to take r and sub it into one of the other ones. I think I will use 1 and 2, and I'll ignore 3 for now. So if I take r and sub it into number 2, plug that in, you're going to see negative times negative 1 is 1 minus k. Bring that across as negative, and k is 1. Excuse me. So technically I use number 1 right here and number 2 right there. Before I can substitute r or k back into the question, I have to check that it verifies in 3. Seems like a pain, but we're going to check. So we're going to verify it goes into 3. The left side is negative r plus k. The right side is negative 6. This seems a little bit boring, but we're going to plug it in, put in the negative, and the k is 1. Negative 1 times negative 1 is plus 1. So that becomes plus 1, and then another 1 plus 1. 1 plus 1 is 2, and wait a second, it doesn't verify. What's going on? They don't verify. But it's supposed to. Remember, these 2 lines are not parallel, and they're supposed to touch. What's going on? Well, you've actually stumbled upon something that is very, very unique and something that we never would have thought of. We have this doesn't work. This does not verify. That means I assumed there was a point of intersection. There was a spot where this equation equaled this equation. Look, I set them equal to each other, but it doesn't work. It's impossible. So these 2 lines don't touch, but they're not parallel. I thought non-parallel lines always touched. What's going on? Well, these are actually 2 very special things that are called skew lines, which I'll explain in one moment. So because they do not touch, there is no point of intersection. So don't forget that. Okay, my final conclusion is there's no point of intersection because for whatever reason, these don't touch. They are called skew lines. And to get a help with this idea of skew lines, I'm going to ask Mr. Lee to step up here and explain what a skew line is.
So what's going on in this example? I thought that if 2 lines were not parallel, they had to touch. So here's an example. You see these 2 lines are parallel. As soon as I tweak one and make it non-parallel, it's got to touch it, right? It's going to touch it at some point. But we just put an example where they were non-parallel, but they never touched. Well, what's going on? Well, this is a special example because we're in 3 dimensions. We can actually consider this case where this line is non-parallel, but over top of the other one. Okay, so I could have it going like this. You can see it's non-parallel, but it's above the other one and never touches. Okay, these are called skew lines. And that only happens because we're in the 3-dimensional space. I could even have them coming down like this. and missing it completely. So they're non-parallel, but they never touch. That rule about having non-parallel and touching is only if they are on two space. So they're both on the desk here. And so if they're non-parallel, they're eventually going to touch. But you could also have a situation where they're non-parallel and above each other or off to the side and also never touch. This is a definition called skew lines.
All right, thanks, Mr. Lee, for giving us that. Here's my little definition that I would put in my notes. Because we're in three space, we're out in three-dimensional world. It is possible to have lines that are not parallel but do not intersect. And these are the skew lines that you just saw in Mr. Lee's video. And he explained this. So I tried to visualize this just for our notes. You see these two lines are not parallel, but because they exist above each other, they're never going to touch. So this example, we did not know this. We thought that there would be a point where they would intersect. And it wasn't until we got to the very end that we found out that it did not verify, which means even though they were not parallel, there was no intersection because they were skew lines. Okay? All right. Catch our breath and do the very last example. All right. So we've got two lines. Let's check to see if they're parallel. Direction vectors here is 3, negative 2, 1. And direction vector there, these are parallel. Okay, great. All right, all three other examples, they were not parallel and they intersected, or we thought they would intersect. These two are parallel. So does that mean they're never going to touch? Well, no, remember from Mr. Lee right at the beginning. Either they're parallel and separate and they're never going to touch, or they're parallel and the same line. So we have to check to see if line 1 is the same as line 2. How are we going to do that? Well, if they are the same line, any point here or any point here would be on the other line. So let's take this point right here. This is the point from line 2. And I'm going to see if it is on line 1. How do I do that? I'm going to take the X, the Y, and the Z, and I'm going to plug it in here to see what I get. So I'm testing point 2 on line 1. So I took my X is 7, put it in right there, equals 1 plus 3k. My Y is negative 2, put it in right there, is equal to 2 minus 2k. And the Z right here, and got negative 1 plus k. And if I solve, you see that this equals k equals 2. And if I solve this one, I get k equals 2. And if I solve this one, I also get k equals 2. Since they're all the same, that means this point could have come from line 1. It actually came from line 2. And since line point 2 is on line 1, then they must be the same line. So they are parallel and the same line. Okay? And because they are parallel and they're the same line, how many spots do they intersect? They intersect all the spots. There are infinite intersections. Okay? And I could do example 5, but I know we're probably getting a little tired. Example 5, I could find two lines that are parallel, and I test point 1 or point 2 onto line 1 and found out they're not the same. In that case, they would be parallel and not the same, and there would be no intersections. But I don't think I need to show you a fifth example to do that. All right, so thanks for sticking with this long video, and I want you to go off and try and do some practice now. Take care.